So, good morning, my dear student. Welcome you to this very important session of electrochemistry. And today I am going to discuss a very important but very simple concept, that is Tafel equation and Tafel plots. And I am sure that you have already studied the most important equation of the electrochemistry, particularly electrode kinetics or electrochemical reaction, Butler-Volmer equation. And I think Dr. Adil has already discussed about this Butler-Volmer equation, which is very important in this particular semester course content. And fortunately, that Tafel equation and Tafel plot is also related to Butler-Volmer equation. So I will not discuss the derivation of Butler-Volmer equation, but while discussing the Tafel plots and Tafel equation, I will use that Butler-Volmer equation, and it is very simple but very important for the examination point of view also. Now this is my system, that whenever I start any lecture related to chemical kinetics or even other, I always suggest my student to refer some of the good books as well as some research paper. If you read thoroughly all those books and research paper, then you could get complete knowledge about this any equation, whether it is a Butler-Volmer equation or even Tafel plot. And it is a physical chemistry concept, so try to understand what is actually Tafel plot and what are the application of the Tafel plot or the Butler-Volmer equation. As usual, you know that I have, because this book is very popular for the M.Sc student and as well as the Ph.D. student, and basically some of my definition or derivation is based on this Atkins physical chemistry. So for Butler-Volmer equation also, you can for derivation of the Butler-Volmer equation, you can rely on this book also, because there may be slight difference actually. I will show you if you see the literature and research papers and other things. So there should be no confusion about this Butler-Volmer equation or the Tafel plots and other things. And I have already told you that this is to my most favorite book, that is Electrochemistry by Philip Rieger, and as the most important book, Electrochemistry 1 and 2, and for Butler-Volmer equation and other things, I have already discussed that electrode kinetics, electrode interface and other things, electrified interface, polarized and non-polarized electrode, because that is also related to some extent that Butler-Volmer equation. So Bockris and Reddy, and of course Dear Crow is also very good book, Principle and Application of Electrochemistry, and a very old book. I think for the last 60 years we have been referring this book, Samuel Glaston, An Introduction to the Electrochemistry. Now in addition to that, because you know that as per the new education policy, one of the important things is that research oriented teaching. That means you must refer some of the very good research papers I'm not saying that you just read complete research paper, but some fundamental knowledge. Today I will also show you how you define the over potential with the help of some very good research paper, how you define the exchange current density, or what is actually cathodic current and anodic current. For that, I have referred some of the very good research papers, and as you know that I always refer the nature and like that things, and sometimes there may be some confusion about the student regarding this transfer coefficient, or sometimes it is called the symmetry coefficient, and exchange current density and other things. Because sometimes what happens, the Tafel plot is considered as a empirical type of thing, but is very important in the corrosion studies and other things, and some large number of electrokinetics studies and other things. So a simple and effective method for the accurate extraction of kinetic parameters using differential Tafel plots, and published in 2021. Similarly, you see that it is so important, Tafel plot is so important, and it is one of the, you will be happy that I have referred a very recent literature, although that Tafel plot is I think 115 years old, more than that, because it was established in 1905 and today is 2024. But you see, this is the American Chemical Society journal, because everybody now is concerned about the energy, hydrogen generation is a very important thing nowadays. So I am taking this literature, the American Chemical Society Energy Letters 2024, a very recent literature of Professor Cooper, and you see that I have taken the front diagram, the Tafel slope plot, because from Tafel plot we can determine some slope values for different types of simple electrochemical reactions, and from that Tafel slope, how can we determine certain things? And see, you see there are some cartoon picture is there. Tafel slope value is kinetically meaningful. Tafel slope value is an arbitrary average, as I told you that it is related to some empirical relationship, and it is nothing but the relationship between the exchange current density or exchange current and the over potential. That is the important thing. So you can plot a graph between the even in over potential and current density like that. So there is a possibility to ask some numerical problem also. Today I will not discuss the numerical problem. What I mean to say that still it is very important. Then you must know something about this Julius Tafel. Basically he was an organic chemist, but he converted into the electrochemist, and he is a German scientist, and this is the first paper, Z physical chemistry, whatever it is in German language, but yes, this is the first paper regarding the Tafel equation and other things, and he published in 1905, and today is 2024, and I have taken these photographs from this Wikipedia like that. He is Julius Tafel, but and this is in 2005 Professor Bastein published a paper, deals with his monumental work on this Tafel plot. So it is 100 years of Tafel equation 19052. So what I mean to say that really it is also very simple thing, very simple. When I complete the lecture, you will find that it is a very simple, but basically why I am showing all this research paper to you, just to understand the subject and the importance of this Tafel equation. Now you can ask me, sir, what is actually, because sometimes what happens in examination side, you will find that there may be a big question, and with that big question there may be a short type of question or short answer type of question. What is the significance of the Tafel plot, or what is actually Tafel equation like that? or what are the significances of the Tafel plot, like that, not derivation. No derivation is required. So that is actually it is a one type of expression. It is a mathematical relationship between the current density and over potential of an electrode. So whenever I am talking about the relationship between the current density or exchange current, so naturally there is a question of the electrochemical reactions. There must be some anode, there must be some cathode, there must be some electron transfer. So naturally it is electrochemical kinetics like that. So that means if I write undo. If I write Butler-Volmer equation, and you are all aware of all these things. If I write, suppose this is the exchange current, maybe there are many forms. If I write exchange current density, you can write, I am using exchange current I, you can write the J, there is no any types of things you can write. It is up to you, small j or whatever it is. So if I exponential 1 minus alpha, then I will say this eta RT minus or in somewhat beta also F RT without considering the anodic current, or suppose I am talking about this, it is anodic A, or even you can directly write exponential alpha A NF and RT. So what is actually Tafel plot? Suppose the value of over potential is very high or large positive. So we can remove this part also. So I'll get only one thing, that I0, or exchange current is equal to exchange current density is equal to this exponential value and whatever over potential and F by RT like that. So there is a mathematical relation. If I take the logarithm value, so now it is very simple, that log of I is equal to log of I0 plus, if I in 1 minus here, if you simply write alpha, so I can write like that, natural log of I is equal to natural log of I0 plus alpha eta F by RT, or even you can write NF or right. So it is a relationship. If I plot a graph between this log of exchange current and over potential, so there may be a slope value, that slope may be 1 minus alpha or whatever it is, and with the help of this we can determine the value of alpha. So this is nutshell, this is called the Tafel plot. Correct. Anyway, I am coming to the other part also. Now there are, as I told you just 2 minutes ago, that why we study the Tafel equation or Butler-Volmer equation, because prediction of specific corrosion related information. That is one of the application. Then of course electrochemical corrosion, corrosion rate, passivity, and molecular electrocatalysis. Electrocatalysis is a separate topic in your that particular unit. So today I am not going to discuss about the electrocatalysis or the corrosion and nothing, but I am just mentioning that these are some relationship between the corrosion and that Tafel plot and other things. Now let me start the things because if I see the definition, so there are two terminology. In one sentence, Tafel plot is very simple, but why I am just concentrating on these two aspects? One is there is a electrochemical reactions, because whenever you are talking about the exchange of the current, so we must be concerned about the interface, electrode and electrolyte. And there must be some, you all know that what is oxidation, what is reduction, where oxidation takes place, where reduction takes place, what happens in the oxidation, what is current, flow of the charges or whatever, all these, you know all these things. But so we must know, we must understand these two things, current density or exchange current density, and what is anodic current density, another is the cathodic current density. Very simple. And over potential, that's all. And ultimately we will come to the conclusion. I am not always, bear in mind that I am not deriving the Butler-Volmer equation, because there is a relationship between the over potential as well as that exchange current density. For that I have to expand the exponential. Suppose we can write this is exponential is suppose x, here is x, here is also x, and the value of over potential is suppose very low, very low. Then if you are a mathematics student, you can understand, if I expand the exponential, 1 plus x, x square 2 factorial like that, 3 factorial like that. And because the value of x is very low, so we will consider only 1 plus x. Then you can get a relationship between the that exchange current and the over potential. That is a part of that Butler-Volmer equation. Don't confuse with that equation. Today I am concentrating only on the Tafel plot and Tafel equation, not more than that. So just I am taking a very simple example. You know that is the redox. Basically, it must be like that. No problem. So you all know these things, and always oxidation takes loss of electron. So if there is a electrode and there is a anode, you see that this is the thing. If I write like that, so if it is a oxidation, so that this electron is coming to this side. So and if it is a reduction, that electron is lost. So it is a very undergraduate level of things. But think that we are using some electrocatalysis in order to enhance the reaction, enhance to that exchange current and enhance that voltage and other things. Then of course over potential and other things comes. But it is a simple, I am taking because whenever I take a complete cell, so there must be some, I can calculate the over potential of this system also. It is a simple hydrogen plus and hydrogen reactions. So oxidation is always, it is an anodic type of anode, there is oxidation, and it is a cathode. So it is related to the anodic reactions, and if it is a, then of course it depends upon the, sometimes what happened, sometimes cathodic reaction is predominant, sometimes anodic reaction is predominant. So sometimes oxidation predominates, sometimes reduction predominates. It depends upon the over potential and other things. I will come to that point. When anodic current is predominant and cathodic current is predominant. I am coming to that point. So, just my first part I have shown you the relationship of Tafel plot, and I have given the equation is like that natural log of I is equal to natural log of I0. That is also one form of the like alpha 1 minus alpha or f and r, isn't it? But here if I just slightly modified that equation, just there is no difference between this and this. I can write like that natural log of Ni minus natural log of I0 exchange current density is equal to alpha Nf, and from that also I can determine the eta also. So what is actually Tafel plot or Tafel equation? In some you can also write like that, because that is the same thing. I will explain. Here I am just showing the relationship between over potential and this, and there are two constants. I will show you that what is that constant, and from that if I plot a graph between over potential and exchange current density, we can determine some slope values also. So the rates of cathodic and anodic reaction, so in somewhere there is the equilibrium, you know that is called the E0 EMF. You know the redox potential of both the electrodes. But suppose we want to modify that reactions. How you modify that reaction? So applied some voltage. That voltage you can raise the voltage or you can lower the voltage. That is the most important thing. So the rate of electrode reaction and the effect of applied potential on the net current, that is also depends main thing. And this, why it is called the net current density? Because we are concerned about the anodic current when over potential value will be positive and large, like 0.12 volt, and when cathodic current is predominant, when the over potential value is less than negative, like that value is minus 1.12 volt. I'll show you these things. Then of course you can, the difference between this is actually current density, that this value of I is the Ia minus Ic. So what is Tafel plot or Tafel equation? Nothing. The relation, therefore I use the term, it is a mathematical relationship, simple mathematical relationship between, there are two terms is important. One is current density, exchange current density, and another is the over potential. So that means you can write also the dependence of net current on the over potential, and we can rewrite that equation like, if I natural log of B natural log of I is equal to eta minus A, and we can write. So I can also write same thing. Now if I see that, if I take the log these things, so I constant exponential n by b. So electrode current increases exponentially with the over potential, and there is a relationship between the exchange current and the over potential in the Butler-Volmer equation. So that is also one form. Now if we are talking about the over potential, again you see that there are different types of formulated Tafel equation. If you see a large number of research papers or other types of books, ultimate thing is same thing, the relationship between this. Again we can write like same thing, it is a constant, or we can call it a slope. So in some books you will find that eta is equal to A plus B, like that thing. So what is the A and what is B? I will explain all these things. So basically, exchange current density over potential, and plus minus. Why we have written plus minus? Because there will be two different conclusions. Again, bear in mind, Tafel plots or Tafel conclusions, there are two. One for higher over potential value and second is for lower potential. So there must be two forms. So now I am coming to that, what is actually exchange current density? The definition of the exchange current density. It is a, of course, it is a transfer of electron. Maybe from this side or maybe from this side. Maybe from oxidation, you know, loss of electron, like that. Loss of electron. So the exchange current density is the flow of charge or the electrons across an electrochemical system in equilibrium. So you can call it a rate of electron transfer process, cathodic current and anodic current. Now I am coming to that, when one is predominating and when one is not predominating. And again I am taking this conclusion from the Atkins physical chemistry book, the very simple derivation they have given. Now if the reduction is dominant, so that means that the cathodic current is less than anodic current and I is less than 0, so then cathodic current is predominating. If IC is less than IA, then if the oxidation is dominant, that is anodic current. And at equilibrium, no current is flow. So the anodic and cathodic current density at equilibrium is called exchange current density. That is the actually at equilibrium condition. And there is a relationship between IA minus IC is equal to the current density. Now I am coming to over potential. Now again and again I am seeing that, you see, again I am taking a very good research paper of Journal of Organic Chemistry, very famous American Chemical Society research papers. And you all know about this over potential and the potential difference in M.Sc first semester course. You know this simple thing, delta G is equal to minus NEF. So same thing, just they have explained that what is actually over, how should I think about the voltage, and what is over potential, establishing an organic chemistry institution of the electrochemistry, like that. So again they are taking this hydrogen simple reaction, most synthetic redox reaction. One is oxidation, another is the reduction. It depends upon that potential. I am giving the specific definition. Like you see, again I am taking three definitions of over potential from three different sources. See, three different sources I am giving you the over potential difference. That means at equilibrium the EMF is E. But suppose you want to raise or you want to low, so we need some external voltage, like that. So therefore it is called the over potential. So the first definition is Atkins, very simple. If the potential difference at the interface, this is actually potential difference because there is the electrode and electrolyte, hydrogen electrode and some hydrochloric acid solution. So over potential eta is equal to E minus E dash. This E is the equilibrium condition, and that E dash or whatever it is, the potential difference applied to the cell. You follow my point? That is actually over potential. Now and normal, when there is a equilibrium, that is called the thermodynamic potential. Okay. Now I am giving the another definition taking from other books. This is Atkins. So the source is, it is a Bardi is also famous book, Electrochemical Methods, Fundamentals and Applications, 2001. So now you see the definition. the additional potential beyond the thermodynamic requirement. Thermodynamic requirement is this: needed to drive a reaction at a certain rate is called over potential. Definition. Last definition. I am using one simple example. Then of course you can understand. Now if we want to change the voltage, so I need some electrocatalysis. Okay. So what would be the over potential? The over potential, the thermodynamic EMF, thermodynamic E minus that catalyst. That is called over potential. The last definition I am taking from another very good research journal. Again, it is M.Sc, American Chemical Society, catalysis. Now that definition is very simple. You see, all the three definitions are exactly same, but in order to make you understand, I am just giving all the very details of that because in Tafel plot, nothing to be worried. Only thing, the relationship between over potential and the current density. That's all. For cathodic current and for the anodic current. That's all. And you plot a graph between natural log of exchange current and over potential. You will get some straight line or whatever it is. So they are taking this hydrogen electrode. So this is the complete reaction. So what is the definition? Over potential is defined as the difference between the equilibrium potential or thermodynamic potential and the potential at which the catalyst operates at a specific current under specific conditions. So this is normal equilibrium state. At equilibrium, we are applying some voltage through electrocatalysis, and that is suppose E catalysis. So the difference is over potential. And this is the complete reaction for the over. I must confess that I am taking the determining the over potential for the molecular electrocatalysis. So again, I just repeat same thing, equilibrium condition and the external source, voltage and change. In second case also same thing, additional potential beyond the thermodynamic requirement, means at equilibrium, to drive the reaction to certain rate. Otherwise, there is an equilibrium, no reaction, no electron flow, no current flow. Now I am coming the last part. There should be no confusion, so that student can. Now why I am showing two equations? Because when I have referred different books, different research papers, Atkins and other things, I found that in somewhere there is a simple equation, and you can follow this equation also, that in the left side there is no problem. Exchange current density, cathodic current, neither cathodic nor anodic current. And in place of 1 minus beta in somewhere, you can write also 1 minus alpha. Absolutely no problem. You can write 1 minus alpha. It is given in the books of Atkins, 1 minus alpha. Then this is NF, maybe number of NF, or you can directly write NF and RT, F by RT. R is the universal gas constant, T is the Faraday constant. And here is also, in place of R, you can write minus alpha. Now, what is alpha or beta? It depends on the particular type of reaction. So when I have seen the literature, I found that it is actually transfer coefficient. Generally value is, most of the cases value is 0.5. So you can write transfer coefficient or symmetry factor also for the cathodic and anodic current. But in some books also, I found that I is equal to I0, absolutely no problem. But in that can be explained in two ways also. That means this part 1 minus alpha this is correct. They have given here A, one is for the anodic part, and this alpha can be indicated with cathodic part. But my suggestion is that don't worry for that alpha or A or C. You can directly write simply 1 minus alpha n f eta, or simply you can write eta f by RT, absolutely no problem. And in some books, what are their literature, that they use that formula, and there will be two conditions. First condition is that if the value of eta is positive, oxidation dominates, so anodic current density plays a significant role. That right hand side part can be eliminated. So there is a relationship between I0, this part, and then you plot a graph between natural log of, if I take the logarithm I, or you can write here IA, natural log of I0 plus alpha just talking that there are two conditions. First condition is, again I am writing same thing, that green law. So eta is equal to positive. So this part is eliminated, anodic current, so I can write like that. And if I take the logarithm, log of I is equal to, you can use log 10 to 2.303 log of I, 2.303, but plus alpha, and you can eliminate this. We are interested in eta and f. In some books that you will find that n, small n, f by RT can be eliminated as the f, simple f, small f. So what you can write, natural log of Li, natural log of I0 plus alpha f, simply f, nf, n small f, that is nf by RT. And if you follow the Atkins, because they actually use that 1 minus alpha. So nothing, you can write here in place of alpha 1 minus alpha. It is a slope value, doesn't matter. So if you plot a graph between, I'll show you that graph. If you plot a graph between natural log of current x, natural log of I, and eta, millivolt and other, sometimes you will get such thing. Slope will be 1 minus alpha f by RT, like that. I'll come to that one. And if the standard value is, I'll show you 1.2 volt, and if it is negative, then of course minus 0.12. This part is eliminated, this part. So we can write like that. In place of natural log I0 there is no change, but here will be minus alpha Nf by RT. So this is the conclusion. And in Butler-Volmer equation, what we do, that because if the sometimes eta value is very low, then of course we'll expand the exponential, and when we solve all these things, we'll get simple same only the relationship between I is directly proportional to this alpha. Everything will be cancelled, so we'll give only Nf, eta and RT. That means there is a direct relationship between this current, exchange current, and this anodic current and the over potential. Now the conditions. So again I am just saying the same thing. Don't get confused. You can simply write, don't confuse with the anodic current or cathodic current. It depends upon the values of the over potential. So it is better if I follow the Atkins book. So you simply write exponential 1 minus alpha Nfn RT, exponential minus alpha Nf by RT. No question of anodic current or X. Then you apply your condition. So there will be two equations, one for anodic current and as for the cathodic current. So first condition is that if eta value is 0, there is no net current density, so no question also there. Again I am taking from the Atkins. If alpha is equal to 0, the cathodic current density is equal to the exchange current density, and it is independent of over potential. Same thing if eta is positive and eta is negative. Second, if alpha is equal to 1, that means the value of alpha is higher, symmetry element. Generally it is 0.5 like that. The anodic current density is equal to the exchange current density, and it is independent of over potential. Or if eta is positive, anodic current density, there is an oxidation state. If eta is negative, cathodic current density predominant, the reduction is predominant. Now I am coming to the last conclusion part. But before that, again I am just, in order to, so that you will not get confused, again I am writing same thing, I0. Again source is Atkins, so that students will not get confused. Exponential 1 minus alpha and eta RT minus exponential minus alpha eta Nf. So simply natural log of I0 plus 1 minus alpha. If I simply write NFRT eta and F, just not. So of course it is anodic current. So see the conclusion. When the over potential is large and positive, the anodic process is dominant, and I is equal to I0 exponential 1 minus alpha Fn. And if I take the logarithm, log of I0, same thing. Second case, when over potential is negative, large negative, minus 1.2, same, just use natural log. I am using Atkins, just I must confess. Natural log of I0 minus alpha over potential and F. F means NF, whatever you want to write, no problem. So again, second condition, when the over potential is large and negative, minus 1 to 1, the cathodic process is dominant. So I is equal to I0 natural log. So I can take natural log of I, same thing, natural log of I0 minus alpha Fn. So if we plot a graph between this, so the slope will be like this, and here in this case slope will be minus alpha Fn. I will show you some plot also. Basically, sometimes straight line are observed. I am not talking about the Butler-Volmer equation plot where you will get such type of things, different types of values changes, like that values changes. That is different thing, natural. That is also over potential, but that is different things. So this is the condition of Tafel plot. So let me summarize the things. First thing is that don't confuse with the Butler-Volmer equation, where I am just giving much time just to tell you about the over potential and exchange current density and otherwise. If you understand the Butler-Volmer equation, so it is the one part of the Butler-Volmer equations. That means you must know the Butler-Volmer equation and then apply the Tafel condition, two conditions, and there will be two forms. So there will be two types of slopes are also there, and this is actually Tafel plots and Tafel equation. But if you want to derive the Butler-Volmer equation, then of course expanding the exponential and other things. Now again, you may think that why there is a difference between that formula, that means when one formula I have seen and eta is equal to A plus B log of I. I am coming to that point also. So that is different, but basically this is the simple plot of Butler-Volmer equation. Now if I just think this plot and take it over. That is also possible. The pen is here. पेन को रीड कर लेता हूँ थोड़ा. If I just take alpha or 1 minus alpha, you can take. N is not required, just RT. N is not required. So what I do, plus alpha and f by RT. Here I need a relationship between this eta and so what I can like that, if I multiply with RT and alpha. Okay, so I will get RT alpha natural log of I. You follow my point? One constant. RT alpha natural log of I0 plus only eta over potential. Or what I can write like that, eta is equal to RT natural log I0. I know what these things. So there are two type of reactions. One, the relationship between this I0 and I3. So sometimes therefore you are getting this natural log of eta is equal to A plus B. So we can give some constant like that. I can give some constant like that. So that is different types of plot. Otherwise, finally you can write this is the actual Tafel plot conclusion, that the relationship between the over potential and the exchange current density. Thanks. Thank you.